Imagine looking up at the night sky and realizing that what we thought we knew about the universe might be completely wrong. What if instead, there's a cosmic timer counting down? And what if humanity is already living past the halfway point? Welcome to an extraordinary new chapter in our quest to understand the ultimate fate of the universe. At the heart of this mystery is dark energy, a force so elusive, it was only discovered at the end of the 20th century. But now, with the help of the most ambitious mapping project in history, the Dark Energy Spectroscopic Instrument, or DESI, scientists have created the largest 3D map of the universe ever assembled. What if dark energy isn't constant? What if it's changing with time, and that change could steer the universe towards an unimaginable finale? Think about it. DESI has tracked the spread of 15 million galaxies and quasars, peering back 11 billion years. If dark energy is really changing, the universe may not expand forever. Instead, it could slow down, stop, or reverse course entirely, collapsing everything that's ever existed into a final, fiery crunch. With global teams poring over mind-bending amounts of data, we're standing right at the edge of a major scientific revolution. The Dark Energy Spectroscopic Instrument has created the largest three-dimensional map of the universe ever constructed. This massive dataset, totaling 270 terabytes in data release 1 alone, represents more spectroscopic information than all previous surveys combined. DESI's precision in measuring baryon acoustic oscillations provides an unprecedented standard ruler for tracking dark energy's evolution across cosmic time. Professor Seshadri Nadather said, "It's not just that the data continue to show a preference for evolving dark energy, but that the evidence is stronger now than it was." When DESI data is combined with cosmic microwave background observations, supernova measurements, and weak gravitational lensing studies, the preference for dynamic over constant dark energy becomes increasingly robust. The Lambda-CDM model, which assumes dark energy remains constant, struggles to accommodate these new observations when all datasets are considered simultaneously. The European Space Agency's Euclid telescope, launched in 2023, is already complementing DESI's work by creating cosmic maps covering nearly 1/3 of the sky. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will extend these capabilities even further. Mike Seifert explained, "Because dark energy is a relatively weak effect, we need larger surveys to give us more data and better statistical precision." The first major theoretical framework proposes that dark energy consists of two distinct components working in opposition. The dominant component involves ultralight Axion particles, hypothetical entities so ethereal they barely interact with ordinary matter yet permeate all of space. As the Axion field weakens below the threshold of the negative cosmological constant, the universe's expansion will slow, halt, and eventually reverse. Nikodem Poplawski has developed an equally revolutionary alternative. Our entire universe may be rotating within a parent black hole. James Webb Space Telescope observations revealed that approximately 2/3 of distant galaxies rotate in the same direction. Just as a figure skater slows their spin by extending their arms, the universe's rotation rate decreases as space expands. This framework suggests every black hole creates a new baby universe, forming a vast cosmic family tree of interconnected universes. Jade's analysis revealed that the number of galaxies rotating opposite to the Milky Way exceeds those rotating in the same direction by approximately 50%. Lior Shamir's analysis identified 33 galaxies with rotation directions, with 23 rotating opposite to the Milky Way, a result with statistical significance of p(0.012). He confirmation of evolving dark energy would necessitate fundamental revisions to cosmological theory. This represents more than incremental progress. It signals a potential revolution comparable to the transition from Newtonian to Einsteinian physics. A negative cosmological constant would connect our universe to anti-de Sitter space geometries beloved by string theorists. Detecting cosmic axions would validate decades of theoretical work on these elusive particles. Poplawski's black hole cosmology would revolutionize our understanding of black hole interiors and the nature of space-time singularities. A universe with finite lifespan fundamentally alters long-term planning for space exploration and colonization. In a recontracting cosmos, far-flung civilizations might one day benefit from cosmic convergence. Sufficiently advanced intelligence might develop methods for transitioning between universe black holes before the Big Crunch. The next decade will prove critical for testing these revolutionary ideas. Laboratory searches for axion particles are intensifying, with experiments like ADMX and Euclid seeking direct detection. The 33 billion year countdown has already begun, marking this era as potentially the most significant in cosmological history since the discovery of cosmic expansion itself. Whether we inhabit a universe destined for heat death or violent collapse will profoundly influence how future generations perceive their cosmic inheritance.